All right, so good morning to everybody. First question, can you hear me? Because this is a different computer than I've used in the past. I'm not sure I got it all set up correctly. Yes, we can hear. Okay, good. Well, it's kind of quiet. That's too bad. You're going to have to listen harder, Max, because I don't know how to boost the audio yet. 3 more people in the waiting room. Oh, how do I let those suckers in? There we go. Admit all. One minute after start. All right, cool. So I'll leave that over there, get it in the way. And let's go ahead and just let any fool that wants to Zoom bomb us do so. So a couple of comments before I start. Now, first thing is the lesson 15 recording failed to upload, and actually the files are lost. I think I can reconstruct them, but that's going to take, based on the 24-hour uploads, to upload a 1-hour-long file. It's going to take a while. I'll work on that as soon as this is over. And then this one, I'm recording using the Zoom software, which I've also never done. So I'll have to see how I can extract that file. And I may not be able to edit it. So it may just be lesson in lab 16, all as a single recording. And we'll just have to live with that. So on the Blackboard, so I should be sharing my screen and you should see my Blackboard. Go look to my YouTube thing and we'll see there is no lesson 15 in the file list for 1330, which I find quite odd because I have a lesson 16 and 15 for some other classes, and I have how to do something in Amazon Web Services, and that all seemed to work. And let me see if I can move the microphone here and make it sound a little better. I'll prop that up on 2 Raspberry Pis. If I had 10 more, I'd have a dozen pies. Okay, so I don't think I need this active. And let's go to homepage. And the lesson collection, down here at the bottom, lesson 16. And today's lesson is a continuation of hypothesis testing. And the laboratory for this week is pretty lightweight. There's no actual assignment, but if you want optional points, you can complete it and upload it, and you'll get a completion score for it. You have an exam on Thursday during the lab session. We won't talk much about that today, but on Thursday's morning meeting, we'll go through a review for the exam before the exam. So the topics are everything since the last exam, although we will re-examine graphics somewhat because we have emphasized graphical interpretation for hypothesis testing. So there's our lesson, and it looks like the server is up and running. Let's check that. Yeah, okay, good, it's running. So I'm not actually going to look at the HTML file other than to acknowledge that it's there. So in our hypothesis testing, we're actually going to take a look at our textbook. Remember that thing, the one that you all go and read twice a week? Oh, no response on that. So either my audio has stopped or, okay, so it's this book called Data 8, and I know that you've all been to the introduction and you know who it's written by. That would be a really good exam question, by the way. Who are the authors of the Foundations of Data Science? And let's go to hypothesis testing. And in the hypothesis testing chapter, which by now you've all read, they had a discussion about the broad speed pump in London during a cholera epidemic, kind of somewhat timely, different pathogen. The question is, chocolate good for you? Although that's really a stupid question. If you enjoy chocolate, eat it. And have the demographics in California change so you can tell the Berkeley bent. And they go into a couple of examples. And the example that we're going to examine is Mendel's pea flowers. So Gregor Mendel, when you take your biology class, they'll talk about him as the founder of modern genetics. Now, Mendel was an amazing biological experimentalist because everything he did, he could classify. He never had things that didn't fit in any classification. And no geneticist since his time has ever been able to replicate that. There's always weird stuff. And so they just put it in the trash can and move on. But he never had to put stuff in the trash can. So it's simply amazing. I'm being kind of cynical here. So what Mendel did is he performed experiments on plants and came up with some laws of genetics, which are essentially still in use, unchanged today. And his favorite plant was the pea plant, mainly because he could get them from Jack, who was a nearby woodcutter, and he had a beanstalk and pea stalks. And as long as giants didn't come falling from the sky, he was fine. And so he would formulate a set of assertions about each variety, and those assertions were his model. And then he tested the validity of the models by growing the plants and gathering results. And we'll switch to our notebook in a second, because I literally copied and pasted and then retypeset everything for the notebook. For a particular variety, he chose a plant that either produced purple flowers or white flowers. And the color in each plant is unaffected by the colors in other plants. Hence, he could conclude that they were independent of one another, presumably identically distributed. And he hypothesized that the plants should produce purple or white flowers at random in the ratio of 3 to 1. So 3 parts purple, 1 part white. So for every plant, he hypothesized there was a 75% chance it would produce a purple flower and a 25% chance that the flowers will be white, regardless of the colors in all the neighboring plants. So it's like a coin that he was flipping, but it wasn't a regular coin. It still had heads and tails, purple and white, but it was weighted such that heads would come up 3 times out of 4. So let's go ahead and assess his model, and we're going to use a simulation approach. So that's pretty much what this whole Data 8 class at Berkeley is about. Why think when we can have the computer make electrons into heat and get numbers out? Also a somewhat cynical comment. So what's going on here is we're going to produce a simulation as if we're growing thousands of plants and see what we observe from that simulation. And then we can make predictions and compare those to the actual data. And our goal is to assess whether or not Mendel's model is accurate. They're using the word good. That's a value term. It doesn't make sense for data science. Whether or not his model is faithful to observations. So we need to simulate a statistic that will help us make this decision. So if the model's good, the percent of the purple flowering plants in the sample should be close to 75%. We don't expect it to be exactly 75% because there is randomness in both real plants and in our numerical methods, but it should be close. So for instance, if we ran an experiment with real plants or computerized plants, and we found out that the fraction of purple plants was about 50%, we'd conclude that 75% is probably not the best proportion. Likewise, if it's 90%, we would conclude it's not the best proportion. But if it's close to 75%, let's say between 72 and 78, we'd say, yeah, that's a pretty good predictor of observation. That is exactly our hypothesis testing mental structure. And the key in this case is the distance from 75% and the actual observation. Large distances are evidence that the model is not faithful. Small distances are supportive of the conjecture that the sample percentage is 75%. So we'll just simply use a absolute value of the sample percent of purple flowering plants minus 75 and use that as our metric, as our measure of faithfulness or lack of faithfulness. And now we want to predict the statistic under the model. So to see how big the distance would be if Mendel's model were true, we can use a function called sample proportions, and now we have to switch to our version of the notebook to simulate the distance under the assumptions of the model. And then first, we're going to have to make a decision on how many times to sample. In doing this, since we're going to compare to Mendel's results, we should simulate the same number of plants that he used. And in his work, in one of his experiments, he kept track of the behavior of 929 plants. So I'm going to guess he planted 1,000 and 71 of them croaked. So we'll have to perform the sampling 929 times. And so we'll follow the iteration model of a few lessons ago, where we first produce something that can generate a single instance, and then we wrap that into a loop, and we repeat that as many times as needed. So we have a single instance, and then we'll sample 929s from the single instance. We will make the proportion into a decimal, either percent or decimal, and then subtract the value 75 from the proportion, take its absolute value, declare that the distance. And so that's our test statistic, the distance between the sample percent and 75. Let's move over to our spreadsheet, excuse me, our oh, what's the password? Oh, there we go. Hey, guy. And we'll let my Jupyter Hub do its thing. And it looks like it's working. So I am in pseudo lesson. Here's the notebook. Please work. Okay, so we've been to the textbook, and that's what I was reading from. And down here, I'm replicating the contents of the textbook. So in the textbook, they use a package called data science. And data science, I'm pretty sure, does not come in CoCalc. To access it on my server, I had to execute this command. So sudo means super user do. -h sets the environment, and then this is where I want to store everything. And then -m means run what's to the right of me as a script. Pip install data science. So in Anaconda, I think just the pip install data science part would suffice. You can't do this in CoCalc because finding and downloading the data science package is not possible in the free version. And so UC Berkeley doesn't actually tell you where the package is. I looked into it the other day. Somehow I found a repository that had a fairly recent copy, around May of this year. So I'm going to import that because that'll let me use their work exactly as written. And I'm going to use the matplot library. So here I've replicated exactly what I was just reading to you, and we're now down to here. Sample 929 multiplied by 100 subtract 75. So what the example is doing is we're going to define a function. We're going to name the function distance from 75 because we're not very creative with function naming, but we'll certainly know what that function does. And what it does is it takes the absolute value of 100 times the proportion p, where the proportion p is what we provided, and then subtracts 75 from it. So all it's doing is it's evaluating, where'd that go? There it is. Let me fix my deal just a little bit. Well, that's sort of an absolute value rendering. Oh, I know exactly what's wrong. So we're also teaching you how to do LaTeX. I think I want to do this. That's better. A little bit of trouble with the spacing. So this is the statistic, and here it is represented in a computer script. To simulate a single value of the distance between the sample and 75% under the assumptions of Mendel's model, we first have to simulate the proportion of purple flowering plants among 929 plants under the assumption of the model, and then calculate the discrepancy. So the data science package from Berkeley provides a tool that will allow us to provide to enter a list that contains model proportions, so purple, not purple, and then it has another function called the sample proportions, where we tell it how many things, what the model proportions are supposed to be, and dot item 0, and it's going to produce a proportion of purple in the sample. We send that proportion to the distance from 75 and have it report back to us. So there's our distance function, there's our proportion function, and we run that, and in this particular instance, because it is running a random number generator, it says that we had a distance from 75 of 0.99. And if we really care, let's see what proportion of purple in sample looks like. I think it's just going to be a single number. Yeah, so the proportion of purple was 0.74. So I'll suppress that, return to the example. And now we want to repeat that 929 times. So we'll make another function called one simulated distance. In that, we compute the proportion of purple in the sample, we return the distance, and then we're going to repeat one simulated distance a lot of times. So for example, this one's going to do it 10,000 times. So there's our simulated distance. There's our 10,000 times. Now let's look at what that would look like. So in the data science package, there's a tool that will generate a histogram of distances. No different than the histograms we've been using, just different syntax designed for people at UC Berkeley, which aren't as good as people at Texas Tech, because apparently they can't figure out how to read like we can. And there's our histogram. And remember, a distance 0 means we were at the correct proportion, and as we move further away, we're more and more not at the correct proportion. And because it's absolute value, there are no negative distances. And this one is, it looks like it's doing the equivalent of a histogram with a density. So we see that most of the distances, we're getting values of 75%, 76, 77, or as low as 73. So somewhere between 73 and 77, which is pretty good. And keep in mind that we generated results that were supposed to be correct. Now, if we look on the horizontal axis,
yes. There was a question that I was not sure how to answer. Can you scroll up a little?
Up.
Here, when it says .item 0, what does that stand for? Is it just a syntax, or?
Well, so the sample proportions is going to produce 929 results, and we're after the first one.
Got it. So it's a way of indexing that. Okay, thank you.
Yeah, there's let's see. I don't have. Let's try this. Let's go ahead and see what the result of this function is. So we're going to print type. A good question, whoever asked it. Proportion of purple in sample. And we just want to find out what the type is, whether it's a scalar or a list or some kind of data frame. Hopefully that'll actually work. And let's just do one repetition because, yeah, one simulated distance. So it looks like the result of proportion of purple in a sample is a float. So it's a single instance, but data science sample proportions, because it produces multiple items. So I guess it's returning model proportions, and has something to do with the count. So imagine if we don't just take the 0th item. Let's see what happens when we do that. I hope I don't regret this. We didn't get the, okay, so data science sample proportions produces an array. We just want the first item in the array. Does that make sense to whoever asked the question? Probably not.
I think so. Let me double check.
But the item is grabbing just the first item in the array. And given that we don't have the source code to the data science package, I haven't rendered it. I don't actually know how this works outside of the example that they provide in their textbook. Yet another reason you should be thankful you chose Texas Tech, because we're apparently too stupid to do Berkeley-style stuff, and so we have to leave ourselves tracks and do stuff in primitive form. So this technique, by the way, for computer scientists, this is called data hiding. It's a standard technique in computer science. It's not unethical or anything. It's intended to hide certain aspects from the user because the user doesn't necessarily need to know them. But in this class, when we're trying to get into the nuts and bolts of everything, it's kind of a disservice. All right, let me see how much other damage I've done in explaining that. I think oh good, I didn't break anything. So here's the histogram of those 929 experiments. If we look on the horizontal axis, we can see typical values of the distance. They're pretty small. A high proportion of the distances in the range of 0 to 1, meaning that for many of the samples, the percent of purple flowers is within 1% of 75%. That is the sample percentage range of 74 to 76. And if we want to compare the prediction to data, we can assess our result. Mendel recorded in one of his experiments the actual number of purple and white flowering plants. So among the 929 plants that he could classify, the 71, those are the ones that came out weird. So he just threw them out. Interesting. So I've just solved a 300-year-old mystery in my mind. Of the 921 plants that he observed, 705 were purple. And that's a proportion of 75.89%. And we can calculate that portion quite easily because this is one of the few things all of us can get our minds wrapped around. No programming required. We take 705, divide by 929, and we get a proportion of 75%. And Farang showed us a really cool function a couple of meetings ago. Let's just round it to 3 decimal places. I sure hope this works. Sweet. So there's our result expressed to 3 decimal places, 75.9. If we want to match Berkeley's one, we'll do that. And if we really care, we can do this. And now we have it. Now we have it expressed in percent. Sure enough, arithmetic is the same even on the West Coast. Now we want to generate the observed value of our statistics. So in Mendel's experiment, he observed a proportion of 75.89. If he subtracts that from 75, he has a 0.89 distance, regardless of whether it's positive or minus. And so we will go ahead and play the same game here. ROUND, our statistic. How many decimal places? Let's go to 4, just because we think that's cool. And I actually want it in I need to leave it in native form. So in 4 decimal places, we get 3/8 and a 1. If we go to 2, I think we should get the 0.89, which indeed agrees with Mendel's observations. So if we were just eyeball the location of 0.89, it's somewhere right about there. And it's in the part of this histogram where there's a lot of observations. And so from a graphical perspective, we could interpret the 0.89 as, yeah, that's a pretty small distance. That's supportive of the hypothesis that 75% of the plants are purple. And we can go one step further and use some of our graphics tools and actually plot the 0.89 on the same plot. So this script, all it does is reproduces the histogram and then drops a scatter plot on top of the histogram. And we're setting the X value based on observed statistic, Y value at 0, but I'm going to change this to, let's see what a 3 does. And keep your eye down here. Oh, that was a mistake. I'll just leave it. I was trying to mess with the plot, but this is the one from the data 8. So the little plot's right there. And so the observed statistic is quite within a typical distance predicted by the model. And by this particular measure, we would say that the data are consistent with the histogram that we generated under Mendel's model. And that would provide evidence in favor of the model. So that's what, yes?
So that little blob above the 1, that's our 0.89?
Yes.
Okay, but
the value of observed statistic on the x-axis, a value of 0 on the y-axis, but remember the y-axis in the histogram is converted to a density. So I was trying to move it up a little bit, and that didn't work out so good. And then the size is 90 pixels.
I don't really understand that, how at 1 that represents 89%.
What's at 1?
The blob. The observed
red
statistic.
dot. The blob is not at 1. I'll go ahead and use their example. You can barely see the blob now.
Okay.
But it's right there.
So what does each X represent? Because
The
in my head,
distance
I think that
between-
represents 1% away from 75.
That 1 does is 1% away from 75. This little red dot is 0.89% away from 75.
Oh, okay. I thought it was 89%, 89% minus 75, which would be 14% away. Okay, I understand now.
0.89%.
Okay.
All right. So that's pretty much what we presented to you all 2 lessons ago when we were doing plotting positions and histograms and comparing histogram plots with data plots. And the point was that was a way of introducing statistical tests. So in Mendel's example here, this is strictly graphical, but it introduces the idea of the elements of a statistical test. And so now I'm going to segue into a more engineering mathematical-like explanation of the same kind of thing, in hopes that one of these presentations will make sense to you. They don't all have to. Once you find one that works for you, you're good. So there are 4 essential elements in a statistical or a data science test. And Farang presented these last lab, and they are the null hypothesis, which we call H sub 0, the alternative hypothesis, which goes by the name H sub A. So you have ho-ha and ha-ha, a test statistic, which we'll get to shortly, and the concept of a rejection region. So let's just go by example. Let's suppose we want to test some hypothesis concerning a parameter named theta, and we're going to estimate that parameter from a random sample, y1, y2, y sub n, and we compute an estimate, and we're going to call that estimate theta hat. So part of the hypothesis testing challenge is the notation, because we're only limited to the letters of the Greek alphabet and what we can typeset. So the parameter theta is what we want to infer about the population that generated these observations, y1, y2, yn. So theta is a population value. We're going to estimate theta by some computation. The estimate is called theta hat. As an example, when we did descriptive statistics, we estimated the population mean by using what descriptive statistic? It's easy. Somebody unmute and answer it. Oh, please, there's 90 of you. Someone knows it.
Repeat the question.
To estimate the population mean, what descriptive statistic do we use from a sample?
Yeah, I would have said the same thing as Max described.
Okay, so Max, describe is just a function. Which of the results of that would give you information on what the estimate of the population mean is?
The mean, right?
The sample mean, yes, correct. And Braden got it. Okay, so let's suppose we wanted to estimate the variance of the population. Again, using just the descriptive statistics, what's our estimator of the variance of the population?
The sample variance.
Kayleen and Ileana, collectively, you're both right. The standard deviation is the square root of the variance. So if you squared the standard deviation, you would have a sample variance. Correct. Okay, so that's what this theta hat is. It's the estimator. Now we're going to assume for this lesson that the estimator happens to have an approximately normal distribution. Vertical. I wonder what I was typing then. With mean of theta and variance sigma squared of theta hat. I think that guy should be hatted, but okay, so this is important before I go on. The estimator's theta hat. We're estimating the unknown parameter theta. We're going to assume for the time being, and then we'll go ahead and do a simulation and kind of support that assumption, that we can, from the estimator, it has its own mean and its own variance, and the estimator behaves approximately normally. So let's suppose that a particular target value of interest is theta sub 0. And we want to test the hypothesis theta, the mean of the estimator, is equal to theta sub 0 versus the alternative theta, the mean of the population, is bigger than theta sub 0. And this picture depicts what could conceivably happen. So on this axis, the horizontal axis, it's labeled theta hat, and these are different estimates of theta hat. So let's say it's out here to the right side, and we collect some samples, and the estimator distribution looks like this little teeny normal distribution here. Alternatively, if we're out here at the theta sub 0, and it's this distribution. So let's do the thought experiment. Let's suppose that our estimator gives us this little bell curve here out to the right, the rightmost one. And our null hypothesis is that the population value is theta sub 0. So is this bell curve far enough away from this bell curve for us to accept or reject the null hypothesis?
Yes.
Yes, to reject. Okay, so Braden, correct. That is so far away from that we would conclude, assuming the sample sizes are the same, and that's fine, that they're too far apart. That's literally what we're saying. And so our null hypothesis that the population parameter theta is theta 0 is not well supported by these observations. So if theta hat is close to theta 0, then we would accept the null hypothesis. However, if theta is much bigger than theta 0, it's quite likely that theta hat's going to be bigger also. So large values of theta hat, bigger than theta sub 0, favor the rejection of our null hypothesis and the acceptance of the alternative hypothesis, which in this case is theta is bigger than theta 0. So using these 4 elements of the statistics test as a guide, we can concisely state what I hope I just said. Our null hypothesis is theta equals theta 0. Our alternative hypothesis is theta is bigger than theta 0. The test statistic that we chose is called theta hat. And in actual practice, theta hat might be a rather elaborate computation. And the rejection region, RR, is we reject when theta hat is bigger than some value of k, is bigger than k for some choice of k. Now the question we want to do is how do we pick k? We go to Kmart, of course, and just buy the one that's on sale, get a blue light special. Now, the actual value of the rejection region is usually determined by setting the type 1 error probability, which we called alpha, and choosing k accordingly, such as in the figure below. So here's our estimator again, centered at theta 0, and we have this distribution, and we're going to pick a value k so that this little area out here is alpha. It represents the probability that we're going to reject H0 when in fact theta sub 0 is indeed the correct estimator. And we have control over k and alpha. If we make alpha big, k gets closer and closer to theta 0, and so any difference would get rejected, and we would have a fairly large probability of type 1 error, which is falsely rejecting the null hypothesis. If we push k far out to the right, where we want to feel that we're absolutely sure of not making a mistake, what's going to happen is we will admit values that may appear to be correct, but in fact are wrong. So we would basically incur a lot of type 2 error. And so there's a balance that we have to choose as analysts. And we want to keep this area small, but big enough that we're pretty confident that the choices we make, notice the word confident snuck into the colloquial description. So now we're going to figure out how to pick a value of k. And what I'm showing here is for something called a one-tail test. Farhang described two-tail, where we'd have another area of alpha here, and we actually reject when we go outside either side. And we can also do a lower tail where this alpha is moved to the left side. They're all same concept. So we'll just look at this one. Okay, so if h sub 0 is true, and theta hat having an approximately normal distribution, bear in mind we stipulated that ahead of time. There's no proof of this. We just said, let's pretend that's so. So theta hat's approximately normal with mean theta sub 0 and variance sigma squared. If we desire a type 1 error probability of alpha, so let's suppose we want to get this value of alpha. And as of now, I haven't set a numerical value of alpha. K would be equal to theta 0 plus the z-score associated with alpha multiplied by the variance of the estimator. And that would be the choice for K. And essentially we're saying is that the probability that Z is bigger than Z sub alpha is equal to alpha when Z is a standard normal variate, our good old friend, the Z-score. So our rejection region can be expressed in the following fashion. The rejection region is equal to theta hat when theta hat minus theta sub 0 divided by sigma theta hat is bigger than Z of alpha. And we'll look how to get Z of alpha in a second. So now our test becomes H naught, theta equals theta 0, H alternative, theta bigger than theta 0. Our test statistic is Z, which we calculate as theta hat, our observed estimator mean, minus theta sub 0, what we think the population mean is, divided by sigma of theta hat, the standard deviation of the sample. And the rejection region is Z is bigger than Z alpha for some value of alpha. And keep in mind, we pick alpha. So we've actually already done all the parts of this. Let's go through a very simple example, including script, to illustrate these ideas. Suppose we're called in as engineers, and we have to contest a shop foreman based on a company policy. It says a machine in a factory has to be stopped and maintained when its defect exceeds 10% on daily production runs. So there's this machine and it makes things. It's making these cell phone things. And once they go over 10%, they have to stop and repair the machine. Because 10% they can eBay those and get away with it, but beyond that, they're going to get caught. So a random sample of 100 items from one day's production turns out to contain 15 defective items. The shop foreman claims the machine has to be maintained and repaired. And so the question is, does the sample evidence support the foreman's assertion? Let's just apply our process and see what we can learn. We'll set Y. We'll keep track of the number of defectives. It turns out that Y will be a binomial variate, taking on a value of true or false or 0 or 1, with probability of any one outcome of P, and the probability of the other outcome is 1 minus P. Again, go back to the weighted coin analogy. So each of these items coming off the manufacturing line is like a weighted coin, and when you flip it, 10% of them are supposed to come up broken, and 90% are supposed to come up good to sell. So let's stipulate that the defect outcome is the value P. And we're going to assume that 100 is large enough so that we can approximate the binomial distribution with a z-score statistic. And again, an assumption that's just stipulated without any backing, but we'll play a little game and see if 100 is suitable. So in that case, our statistical test can be summarized as H0, the defect proportion is 10% versus the alternative hypothesis, the defect proportion is bigger than 10%. We've stipulated that a test statistic of Z, which is equal to the observed proportion minus the target proportion divided by the square root of P0 times 1 minus P0 over N, and that's just the binomial representation of standard deviation. You look that up in a statistics book or get it off the internet like I did. And our rejection region is Z is bigger than Z alpha for some value of alpha. Let's choose a value of alpha of 1 part in 100, 1%. So that's our probability of rejecting the null hypothesis when in fact it's true. And now we need to find a value for Z sub alpha. So this is the crux of the exercise. So we'll do it for this particular example. So we'll import our math tool, and I'm going to define a function called norm distance, which is exactly from a prior class. And we're going to take 100 things off the production line. So that'll be what we call our sample count. And of those 100 things, we're going to determine which ones are defective. And for this example problem, there were 15 defects. We're going to compute our estimate of defect rate as the ratio of defect count to sample count. So I'm calling that P hat. And then our P0, which is this P sub 0, is declared at 10%, 0.10. So that term right there corresponds to the P0 here. And P hat right there corresponds to the P hat in the test statistic. I'll go ahead and calculate the value of the test statistic, which is P hat minus P0 divided by the square root of P0 times 1 minus P0 divided by the sample count. So essentially this expression right up here is the test statistics. Now the trick is we need to find the value of Z alpha, the rejection value, so that alpha equals 0.01. And we actually did that a couple of lessons ago when we were producing quantile functions. Recall that the norm distance function returns a quantile integrating from minus infinity to infinity, but in fact we want to go the other direction. So we'll simply subtract the quantile from 1, which will give us the right hand tail. Think of it as integrating in a negative direction from plus infinity to minus infinity. So 1 minus the norm distance of Z alpha gives us a quantile. And so we want to set that quantile so that its value is 0.01. And then once we've done that, and so here it says, here we find by trial and error. Now, obviously, I went ahead and poked through until I found a Z alpha of 2.325 produces an alpha value of 0.01. And now we perform our test. If the value of Z test is bigger than Z alpha, yep, that's our rejection region, then we're going to reject the null hypothesis. And we generally report all the other stuff we did because we're getting paid $400 an hour for our programming, and so we've got to make it feel that we've earned our money. If that's not true, we'll print do not reject and report the test statistics. And let me suppress this output for now, and I'll explain that in a second. Okay, are there any questions conceptually what's going on here? Yeah, Brandon, I realized that after I chose the variable name, but I did not bother to change it. So you need to try to wipe that out of your brain for now. That's fine for when we're not in class together. Let's see if there's any other. Pretty sure he said yeah. Okay, I think we're caught up. All right, so I'll wait a second and let's refresh everything. Our norm distribution function from a couple of lessons ago. The various inputs for sample count, defect count, p hat, p0. the actual test statistic, a little bit of mumbo jumbo to produce the Z alpha or the rejection value, and then the statistical test and the automated interpretation. Does that make sense before I go run it? Max has a question too.
Guys, ask your questions.
Yeah.
Where
Where
did the
did-
defect count come from?
The defect count came from right there. One day of production had 15 defective items. Sample count came from right there, 100 items.
Dr. Cleveland, you said that you found Z alpha using trial and error. Is there a particular formula that was used for that, or
Sure,
like
we'll go
did
through
the
that.
Yeah.
Let me suppress the output and we'll go do the trial and error. Okay. Okay, so here's what we'll do is I'll guess values for Z alpha and we'll see what the, so, okay, what I'm gonna do is I'm gonna be guessing values of K essentially. So I'll pick different values of K and it's gonna return the shaded area alpha. So how do I do that? I'm super lazy. So let me get my syntax error fixed. So I have a question for you. Somebody choose a value of K. Now we're sampling from a standard normal distribution. So the mean is 0 and the variance is 1. So every value of K represents the number of standard deviations away from the mean. So let's make our first guess a 0. So what do you think the area alpha is going to be if we made our first guess right at the middle?
Would it be at standard deviation?
I'm going to put 0
would
in
it be
for,
at
okay, I'm going to put, so think of what I just at 50. Okay, someone said 50. So you actually meant 0.5, 50%. Let's go ahead and see if that's true. Okay, do not fail me now, computer. So 0.5, sure enough. Now let's move to 1. We'll put K equal to 1. So that represents 1 standard deviation away from the mean. So how much area is going to be left? 1 standard deviation is 66%. So what's left is 34%. It's going to be half of that because, yeah, Ileana, we're actually just building a Z-score table. 17, I agree with the 0.17. So let's try that. We'll go ahead and make this a 1. 0.158, so close enough. Now let's go ahead, 2 standard deviations, which is 95%. So that's going to be 47, be about 3. 0.02, 2%. No math, Z alpha is what we pick it to be. And so let's go 3 standard deviations. And now our alpha is, if we multiply by 100, it's 0.001. And we're shooting for an alpha of 0.01. So I think 2.5, 0.006. Let's go 2.2, 0.0139, 2.3, 0.0107. We're getting close. And I'm going to go ahead and cut to the chase. And there's how I found by trial and error. And I have some passed here, but I hit my Z alpha value that will produce a value of alpha of 0.01. And that's literally all that's going on.
Okay. And then so is that just is it going to be dependent on like what your samples are? Like would that number that we guess, is that going to be different like for every like set of values?
It's going to depend on the probability distribution of the test statistic.
Okay.
So if a test statistic is distributed standard normal, then we can use this number. If it's distributed students T, we'll have a different value. If it's distributed chi-square, we'll have a different value. If it's distributed gamma, we'll have a different value.
Okay.
But we can determine it, we determine all the same way. Okay, so we're going to stick with that Z alpha for the time being. Let's go ahead and reactivate our test stuff. Hopefully that will work. So now it's going to perform the test and tell us whether to reject or not. Remember the shop foreman said 15 defects out of 100. We need to shut down and rebuild the machine. However, the test statistic is not supportive of his claim. The test statistic is 1.67. Our rejection value is 2.325. Our type 1 error probability, which we determined ahead of time, is 0.01. And our null hypothesis was that the proportion was as expected. So that's basically a hypothesis test. Is that clarified any? Because I want to go on to the next part, but this part has to be clear.
Yes, thank you so much.
We choose alpha. From alpha, we determine a Z alpha. We got that in this case from the normal distribution, and then we perform the accept reject. So that's straightforward. Now, last time we also mentioned the p-value. So the p-value uses the same tool that we use to infer Z alpha, except that instead of prescribing alpha, it tells us the amount of gray shaded area under the curve at our particular test statistic value. So in our case, our p-value is going to have more area than the 0.01. And the usual for that calculation is simple. Now we're going to just print the p-value at rejection. This is the usual terminology. So what this terminology means is if I decide that the test statistic I calculated, what's the p-value if I declare that the rejection value? And that's a somewhat quicker way to interpret the results without having to do this trial and error mumbo jumbo, especially when you have distributions other than normal, which are somewhat hard to evaluate. So all we're going to do is we're going to put the value of Z test into the normal distribution instead of the value of Z alpha, and we'll compute a quantile associated with that. We're going to call that p-value, and then we're going to report it. So I report that, and my p-value at rejection is 0.04. So it means we wanted to reject at 0.01, but we have a 0.04, almost 4 times as much area. So we're somewhere over here. And that can be used as a different way to interpret. So the p-value at rejection is almost 5% versus our target rejection value, which was 1%. Let's see what the defect count would have to go up to get rejection. So let's say we take 100 things and we find 19 defects. My question to you is 19 defects enough for us to declare the machine broken?
No.
I don't know. How do you come up with no? You
Yeah,
remember?
it should be because we only want 10 defects until we have to repair it.
So how do we defend that? I press run, right, and see what we get from the statistics test. Actually, you guys are playing into my script perfectly. So we'll just rerun the test. If we have 19 defects, it says reject. It says our test statistics 3, reject is 2.3, type 1 error probability is, and the p-value at rejection is 1 part in 1,000. So it's very unlikely that we would observe 19 defects in a sample of 100 if the machine was working right. Let's go to 18. So we'll do a little bit of p-hacking here. 18, we still reject. 17, we reject. 16, we'd accept. So this actually introduces something a little interesting. We want 10% failure rate, but our current testing protocol will let as many as 16 get through, and we keep the machine running. So what can we do to change that? Bigger sample.
Your alpha.
We can change our alpha. Yes, correct. So let's I can do that directly because we're printing. So we can adjust this type 1 error probability. So which way would you propose changing it, Ileana?
Like what should the new Z alpha be?
Yeah.
Like lower, so like maybe 2.05. Okay, yeah.
Let's go. Let's see what happens if we jam that thing that way. That may be the wrong direction. Okay, that's a pretty low alpha.
Yeah, it's gonna accept more.
So let's do that. $12, do not reject. So we're now down to 14 would cause rejection. And so again, we can go to fewer standard deviations. We'll just go to 1. And let's go down to 10. I think 10 we will do not reject. 12, do not reject. So what we're doing right now is called p-hacking, and generally it's not necessarily considered the most honorable thing to do, but that's how we come up with a suitable rejection value. So now we have it, our defect count at 14, and the p-value at rejection is 9%. And so generally modern data science, while we'll report type 1 error probabilities, most of the decisions are made based on the p-value at rejection because it gives a little bit of operational flexibility to make a decision. Now let's take a look at the defect distribution by simulation. Let me return this back to all of its prior glory. And we'll go back to our 15 defects. There we go. So let's go ahead and just simulate this machine. So we're going to have a function called sample parts, and we're going to tell how many things to take off the production line and what the failure proportion is supposed to be. We'll create an empty list, and we're going to use a random number generator from the random library and go uniform on the range 0 to 1. And I'm going to declare that if the value of a sample is less than the proportion, I'm going to call that a fail, and I will append a 0 to my sample list. And if that's not true, that was a marketable device, and we can sell it, and we'll put a 1 to our sample list, and then I'm going to return the sample list back to the calling program. And then I'm going to create an empty list called defect rate, and I'm going to play a game. Would you like to play a game? Yes. How about global thermonuclear warfare? How about a nice game of tic-tac-toe? So I'm going to make a series of samples. I'm going to sample first 1 item, and then 2 items, and then 3, and then 4, and so on. And I'm going to keep track of the defect rate from each of those samples. So if I sample a single item, I'm either going to get a defect or I'm going to get a success. And the probability of defect is 10%. Probability of success is 90%. But in that 1 sample, I'm either going to get a 0 or 1. When I do 2 samples, I'll either get 2 zeros, 2 ones, a 0 and a 1, or a 1 and a 0, 3 samples, and so on. And so I'm going to keep track of each of those as a defect rate. So if I do the single sample and I get a defect, my defect rate in that sample is going to be 1. If I take 2 items out and 1 of them is defective, my defect rate is going to be 0.5. If I take 3 items out and 1's defective, the defect rate is going to be 0.3, and so on. And so I'm going to keep track of all these defect rates, and then I'm going to plot them in a histogram. So if I don't take very many samples, if I only sample 10 items, here is what my histogram is going to look like for 10 items. I'm not very definitive. We got 6 of them. Looks like they came up defective. We got another place that has a rate out here of 10%, rate of 15%, one at 0.35%. So the zeros are not defective; those are acceptable. So our defect rate in a sample of up to 10 is either 0, 0.11, 0.14, 0.34. Not very useful information. Mostly 0. So I guess all we can conclude from this is that the defect rate is less than 50%, which in the software industry would be good, but it's not very good for making widgets. So let's go ahead and take up to 50 samples, play it again, and that's not a lot better. We're either getting a rate of 0, or we're getting stuff somewhere between 0.05 and 0.2. So we know that the defect rate is somewhere in this region. Notice not much bigger than 0.2. Let's take 70 samples. And that's kind of sort of looking like a distribution. It's sort of peaking here, and again at 0. And we'll keep getting those zeros for a while because we're not sampling enough things. Let's go up to 90. Because you got to bear in mind, every one of these phones we take off the manufacturing line, we have to give away. And we're running out of radio stations at the time of 90. Starting to have some sort of distributional shape. We've still got a lot of influence of 0. Let's go to 100, which was our particular test. And now it's sort of looking like a probability distribution. And that's coincidence that 100 was the magic number. But the question I want to ask, so the defect rate is our test statistic. Is it starting to look normally distributed?
Yes.
Yes.
Yeah, it's starting to look like a distribution. Let's go ahead and do 1,000. Looking more like a distribution?
Yes.
That'd be a yes. See, I had notes 2,000, 3,000. We'll do 2,000. We're going to start to hit the limits of the machine to do it in a human amount of time. So it's starting to look more like the Empire State Building. and we'll go to 3008. Well, that's close enough to 3, and that'll take a while. And I don't think I want to go beyond that. So we're waiting on the little squirrels to sit there and flip coins. It's telling us that they're busy. And there's what would happen if we could sample the statistic 8,000 times. And so our earlier conjecture that we think the test statistic is approximately normally distributed is well supported by this simulation. Now in practice, we're not going to destructively test 8,000 things on a machine. And what the data scientist engineer would do is we want to find the smallest number of daily samples we have to use to get a plot that kind of looks like that, accepting that there's going to be some deviations on either side of that, but still guaranteeing the assertion that it's approximately normal. And so the one that was used in the example that I took out of a textbook that was written before. So this is what our 100 sample looks like. So we're going to get a fair amount of, actually, let me turn density to true. It'll start to look better. I think that will, yeah, we still have an awful lot of influence of being able to take a sample and have no defects, which I guess is good from a manufacturing perspective, but the information we have on the actual defect rate is still contained in this part of the histogram. In the lab, Farhang is going to show you a way to get a smooth representation of this histogram on different set of information. But that is the essence of hypothesis testing. And I hope that you come through today realizing it's not actually terribly hard. Now, admittedly, this null hypothesis, alternative hypothesis, no brains required. The test statistic might take a little thinking depending on the context of the problem, and the rejection region is usually the hardest part to figure out. And then finding the Z alphas, if it happens to be Z-score, takes a little bit of ingenuity to use the tools that we have. But conceptually, a hypothesis test is not particularly difficult. Now, moving on, there's a concept called A/B testing. You see there's nothing down here, so you're almost done with me, and that'll be good for you. In data analytics, one of the challenges is deciding whether two samples come from the same underlying distribution or not. And that's called A/B testing. And the name comes from the labels of the two samples, A and B, because again, data analysts and data scientists are not terribly creative when it comes to naming. Funny they don't do ABC, because that'd be easy as 1, 2, 3, but then of course you'd have to pay royalties to Sony. We've actually already addressed this kind of comparison, and we'll do more in the laboratory. And in fact, we went quite a bit further than is normally done when A/B testing is presented, in that we even postulated the particular types of data models that explain the data. So as of today, you have been exposed to enough hypothesis testing for you to be defective to the end of time. Just kidding. Are there any questions before I hand this over to the laboratory session?
Nope. Yeah, so this is going to be on
Okay, cool. Well, so pardon?
This is going to be on the exam, right?
Yeah, with an alpha of 0.2.
All right.
Yeah, this specific question probably won't be on the exam, but yes, on the exam, you are expected to be able to interpret and employ hypothesis tests as we've shown you in the laboratories.
Yeah, not this particular question, something tougher and more complicated.
Yeah, this was just too easy for you. Okay, well, if you want to visit it on your own, there's the notebook is on the content server, and if you just want to look at the notebook, I think run once. Oh, I hope I don't regret what I just did. There is a HTML file. So the only thing on the HTML that doesn't come through is it doesn't typeset the mathematics correctly. So all this weird stuff here, that's how it made that pretty mathematics. But you can view that from anywhere. You can see that on your phone. To look at the notebook, you have to run the notebook. Okay, I'm going to turn over the lesson to Faring, and he will walk you through the lab. I think we'll take the usual 5-minute break.
Yeah, we can do that. But I'm going to be
Okay.
sitting here if you have any questions or concerns or horror stories to tell about the exam to come.
You are the
Well,
host, dude.
thank you. Now that you, I'm reading in the chat box something about curving the test. I saw something very funny the other day.